Okay, I think we're ready. We're going to do some basic measurements. Actually, we're going to start with a tool, so a multimeter. A lot of the course has to do with sensors and electronics and things like that. So I'm actually going to start, and I thought I'd do this every class period, is to pick a different tool that you use to measure things with and show you how to use it the best way. So today's tool will be the multimeter. And then once we do this, we'll get into Python and a little bit about how to begin to create graphs and plots and things like that in Python, assuming you don't really know much about Python. So this is, there are all kinds of different multimeters. This particular one is one that auto ranges, so it goes in and it doesn't have as many options on the dial here as some you might see. Some of them might have a lot of different options for measuring different ranges of voltages and things like that. This one, you tell it what type of voltage or current or resistance you want to measure, and it automatically selects the ranges. So this one won't work exactly the same way as one where you need to tell it which range of voltages you're looking for. Other than that, it's going to work pretty much exactly the same. First of all, let's see. It normally comes with a multimeter. Normally comes with two leads. I'm trying to get them untangled. They're all tangled up and stuff. So on one end, they'll have something that's going to plug into the multimeter, and on the other end, the default is something like this. Just two little probes. They're usually colored red and black. Red is normally the positive one. Black is normally the ground, or the one you might call negative. Normally there are three, let's get that in the screen. There are three places you can plug them in. The black one's pretty obvious because there's only one of these that is black to actually plug into. They're not always color coded, but a lot of times they are. And this one is usually going to plug into COM. You can see that in there. That's common, and it's the ground. Sometimes there'll be this little symbol. You can see that those three lines stacked on top of one another. But the red one, there's two options a lot of times. One of the options is going to have something to do with measuring a higher current. So this one, you can see it says T10A, so that's 10 amps, and it says it's fused. So there's a fuse inside of the multimeter that can burn up, basically, if I try to measure too much current, and it'll protect the multimeter, the actual electronics in there. Normally we're not going to use that one because, particularly in this course, we're not going to be measuring 10 amps. That's 10 amps is a lot of current, so we're not normally going to be measuring the 10 amp side. The other one, in this case, it has, hey, if you want to measure a voltage or a resistance or continuity or a diode or capacitor, what are you trying to measure here? This one doesn't say what the current limit is on it, but it's usually way less than 10 amps. So we're going to use this set. And then on the dial, you'll have a whole, like I said, lots of options on some multimeters. This one has a couple of different ones that you see a V in, so you can assume those are voltages. But the sine wave over the top, let's see if we can get closer. There we go. The sine wave over the top of them, there and there and there, that is going to tell us that that is primarily for measuring an AC voltage or current or whatever. And that's going to be the power that comes out of a wall plug or something like that without being converted over to DC, like a battery or a power supply or something. The ones that have the straight lines, and this one's straight and has a dotted line underneath it, those are going to be for measuring DC currents. So batteries and power supplies, something you plug into a wall, but then it has that block of, I don't have one with me right now, but a block that plugs into the wall and converts the wall alternating current over to a direct current like a battery would. So a phone charger, for example. We're going to only use DC measurements in this course. We're not going to mess with AC. AC is the one that is much more dangerous than a direct current type deal. So we're going to use this one if we want to measure a voltage from a battery. Here, this one is just if you're trying to measure smaller voltages. So it's not fully auto ranging, I suppose. I guess it does have a separate option if you're trying to measure really small voltages. That might be handy when we get later towards the end of the quarter and we're trying to measure some voltages off of a bridge circuit connected to a strain gauge that are really small. But most of the time we'll use this one. So if you're trying to measure 3 volts or 5 volts, this is a good one. DC. This is the omega symbol, so that's what we use for ohms. So any kind of resistance measurement, I want to measure the resistance of one of these resistors I've got plugged in. I'm going to put it over here. A lot of times there's going to be one that has something that looks like little pulses or whatever. This is supposed to be a sound. So this is a continuity check, and what it does, you put it over here, and if the leads detect continuity, in other words, they detect a connection between point over here and point over here, then you get a sound. And so that is just for trying to determine you've built a circuit and you want to make sure it's all connected. Is this point connected to this point? No, I'm not getting continuity there. Why am I not? That's actually kind of, because this is not connected on the other end here, so it doesn't have continuity, see? So no current could flow through here, basically, because the circuit isn't connected over here. If I move this over, well, it measured a resistance, but it's not giving me a continuity. Oh well, we'll deal with that later. A lot of times it's just checking, is there a connection between these points? This one is if we're trying to check a diode, and then here are current measurements. So voltage we'll use, current we will maybe use a little bit. It's not as common. It's a little more difficult to measure current in a circuit. You have to take part of the circuit out to measure current. And I have the same options here where I have a AC and a DC current. Again, we're only going to use the DC side of things. All right. Let's just do some resistance measurements first. So I've got a whole set of resistors here. You'll notice that they have different color codes on them. And, well, there we go. This one happens to be brown, black, red, gold. Maybe if I turn it this way, that'd make more sense. So brown, black, red, and gold. Those stripes on there tell the reader, assuming you know the code, it tells you what the resistance should be for this resistor. So brown, black, red, and then gold should be a 1, a 0, and then 2 more zeros. That's based on the color codes. We don't really need to understand those right now. Maybe they'll be part of the course later on, but so this should be 1,000 ohm, and then the gold is a tolerance. So how close to 1,000 ohm can I expect this to be? So there's different colors like gold and silver, and then no band at all. The gold one should tell me that this is in plus or minus 5% of 1,000 ohms. So if I want to find out what is 1,000 ohms, is it actually 1,000 ohms, then I would connect it to my multimeter here, and it tells me 980 or 0.983, and then you can see over here, well, I can't point and hold everything at the same time. It says kilo ohms, so that's thousands of ohms, so it's 982 ohms or 0.982 kilo ohms. That's really close to 1,000, and you already see some of the issues with measuring. So which one of these do I trust? Do I trust the multimeter? Do I get another multimeter to test this multimeter? Do I trust that this thing is supposed to be 1,000 ohms? And so there's already that uncertainty creeping in. I don't know. I suppose I could probably look up the data sheet for this multimeter and find what kind of uncertainty is associated with it. And then I know a little bit about the uncertainty associated with this resistor. It told me on the resistor itself that there's a plus or minus 5% tolerance. But you can start to see, how do I know which one is right? And if I want to check the measurements of this, how do I check it? Do I get a more expensive multimeter? Do I get a whole bunch of multimeters and measure? What do I do? So next class we'll actually talk about how some of that works and how do you go and check to determine which one's the right measurement. let's do a couple of others here. Actually, these that I built into this circuit, they're all 1K, 1000 ohm resistors. Here's another one that's not. Let's see what it is. So this one is brown, black, yellow, gold. So the only difference is that third stripe, instead of being on these, it was red, right? Yeah, it was red. This one's yellow. So the brown is still going to represent a 1. The black is still going to represent a 0, but the yellow is not going to be 2 zeros. When I measure this, I have 93 kilo ohms. So I've got a much different, I've almost got 100,000 ohm resistor here. But on the outside, other than that one stripe, they're the same size. They even look mostly the same. It'd be easy to confuse the two of them, except for that one stripe in there. So it's kind of how the resistors work. There are other formats for resistors. Sometimes there'll be a blue color. That just means that they can handle a different amount of current through them. Sometimes they'll be in a block. Sometimes they're little tiny things that go on the surface of a chip. I don't see if I have a chip handy to show you. Maybe. Let's see what's on this one. Well, some of these little guys in here are little resistors. There's different formats for them. The ones that we'll use in this course are pretty much this more common form that you would see. We'll use them because they plug in nicely to this is called a breadboard. In the really old days of electronics, you didn't have these nice plastic prototyping boards, and so people actually took a breadboard, like a board you would set a loaf of bread on, and slice it up, drilled or nailed some nails into it, and used those as point-to-point contacts. And so that name of breadboard kind of stuck. And this thing, a lot of times you'll call it a breadboard or a prototyping board. The nice thing about it is that you can just plug things into it. You do have to understand how points are connected on here. That's not really what we'll talk about today, until we will talk about that when we actually need to build a circuit. What I wanted to show you with this is that you do have to be careful when you're measuring things, particularly resistance, in a circuit that you've built. So for instance, actually right now, if I try to measure, just gonna get it all on here. I think so, like that. If I try to measure this, I'm still on the ohm, still in the same setting that I just used for, here's one, 9.8 kilo ohms. So this is a 10K over here. And when I'm doing DC, actually I'm doing resistance measurements. When I'm doing really low voltage, it's okay if I hold these like this, not going to hurt me. The multimeter does actually send a very tiny current through there to get a measurement, but it's not going to be anything. And I probably do affect it by holding, because I become part of the circuit then. I do have some little spring clips for the end of these, but I couldn't find them. So I've got to find those, because they make things a lot easier when you can just clip the leads on here versus having to hold them the whole time. So here's one thing I wanted to show you. If I try to measure this resistance here, so these two, well, let's just confirm. Here's one of them. They're the same. They look a little different because they're different brands, but they're the same pattern. So that's another 1K. And so is this one here. They're both brown, black, red, gold. But when I put it into the circuit and I measure it, same resistor, I get 494.1 ohms. So I get 500 ohms. And that's because I'm not measuring, even though I put my leads right across, I can get them as close as I want to the resistor. I'm not measuring the resistance of this element. I'm measuring the resistance between this point and this point, which when I've plugged it into the circuit has other things attached to it. In particular, it has this 1000 ohm resistor in parallel. These two resistors are in parallel. And if you remember about resistors in parallel, basically what they do, these two both are 1000 ohms. And so the equivalent resistance of these two would be 500 ohms, which is what I read. I read 494 or whatever, 494.4. So be careful if you've built a circuit and you're measuring resistance in the circuit as it's built. There's a good chance that you will not measure what you intend to measure, because you're actually measuring the equivalent resistance at that point. and not necessarily the resistance of the element that you're trying to measure. Voltage is okay. Actually, well, until I plug some voltage into here, I'm not going to have anything. So I've got a little power supply sitting over here. Let's connect it. Let's see, I've got this one. On this breadboard, this blue line has a little negative sign and it runs all the way down. These are power rails. The blue one I'm going to connect my negative lead from the power supply to. And then the red one, and I'm doing it on the other side over here. The red one's the same thing, except I'm going to connect the positive lead to it. I'll turn the power, let's get these out of the way so they're not covering up stuff. Let's just put 3 volts, well, 4 volts through it, since that's what my power supply is very sensitive over here to be able to adjust. 4 volts. So it doesn't do anything, it just sends 4 volts. I guess it's basically a really, really bad heater. Eventually these things might heat up a little bit, but it's running 0.02 amps through it right now, so not hardly anything. So again, this voltage measurement is not going to give me any meaningful thing because it's going to be a AC measurement in a DC circuit. So I want this one, and I should be able to measure the voltage across any resistors. There's 1.7 volts of my 4.2. Here is, well, all right, so I got a negative number here. So negative voltages are just because I have my leads backwards. So if I flip them the other direction, then I get a positive voltage. I probably had a negative the other way too. I just didn't pay attention to it. And there's 1.7 again, and 0.8. So 1.7, 1.7, and 0.9, if I add those together, I get more or less 4.4. I didn't look at the decimals to see how close I was, but my power supply is showing that it's outputting 4.4 volts. And so that would be the voltage in a closed loop on my circuit here. So I can usually measure voltages without any problem. Resistances, I have the issue that, you know, this is a 1,000 ohm resistor, but when I measure it, actually now I've got power running through it, so I'm not going to be able to get any measurement. It's confused on what's going on here. It just gives me this 0L or negative 0L measurement. That's telling me that the multimeter cannot figure out the resistance of this resistor while there's other current going through it. What it's expecting is there's going to be a little potential across these leads from the multimeter, and then it can figure out the resistance from that. But there's other current being supplied through the power supply. Now if I turn the power supply off, I should be able to read. Now we're back to reading. Now we're reading a different number than before, but it's changing, right? That's another thing with electronics and measurements. They heat up, and even though it doesn't look like it's doing anything, there was current flowing through here from the power supply, and it did heat these elements a little bit, and the resistance of elements change when they heat and cool. And so you could see it changing. It's probably back to normal now. Well, no, it's still going. You know, there's a little bit of residual heat there that is changing that. The current measurements are trickier though. So with the voltage measurements, you can measure in parallel to what you're trying to measure. Current, you actually have to send this current through the multimeter. So to do that, you can't do this kind of thing. You have to actually, if I want to know the current, let's say in this resistor, I have to take it out of the circuit, put my multimeter in series with it. There's no voltage on right now. Let's turn something on so we get some kind of measurement. And put the, well, I've got such a low, it may not supply, my power supply is protecting itself here and not providing anything. So, but normally you would have to put the leads of the multimeter in line with the circuit in series with the element that you want to measure. So you actually have to take it apart. I'm not going to get any measurement off of this particular thing right now though, because it's not going to send infinite current through there right now. But that's, oh, actually this multimeter might have a problem. If you do get readings that don't make any sense, most of these multimeters, now that I remember, I think this multimeter has a blown fuse in it, and I never did change it. So there's not only this fuse for the 10 amp side, there's usually another fuse for this side for the current measurements, because they are very easy to blow out if you don't do them correctly. I don't know if I can get it open fast enough. We might have to do that next time. This one's got a coating on it that you have to get out, and so there would be, yeah, just these, probably these two and that screw to take this cover apart. This one doesn't have a panel that you can just remove, but there's a fuse inside of this multimeter that protects it whenever you do make a measurement that would send infinite current through here. Like a lot of times you try to measure a current and you accidentally put it across here versus in series with it. That puts the multimeter in parallel, and the multimeter when it's measuring current, a lot of times that will blow that fuse out, and I think that's why I'm not measuring any current on this one. So if we have time at the end, maybe we'll open this up and see if we can see the fuse in there. Mainly, we're not going to do many current measurements. We're going to do voltage measurements, which are pretty straightforward. But we'll also do resistance measurements, which are mostly straightforward, except you can fool yourself when you are measuring in the circuit itself. So the power has to be removed from the circuit, and you have to be sure of what equivalent resistance you're actually measuring versus, you know, are you measuring this resistor, or are you measuring the combination of these two resistors or whatever. So just wanted to show you those things with this. And now let's go over to some Python. So let's get this out of the way, and let's put Python up here. There. All right. So this is the piece of software that I told you about before. Well, if you saw the previous lecture, it's Thonny, THONNY.org. If you've never done anything in Python before, then it's a good starting point. You don't have to do a lot of setup, almost no setup. In fact, you just go download it, and it does all the setup. There's one button when you first run it that has a little pop-up screen, and it says what language do you want to use, and one other option on there. You just keep the defaults. Unless you, for some reason, do want to change the language, but I can't remember the other default, and it won't show me now because I've already went through that. But that's the only setup screen. You pick where you want to install it, and then it has two options for the first time you run it. And then after that, you get this screen. So most of your coding happens over in the big block over here. And now I will say that mine started out and it was, you know, a much smaller window, so I made it bigger. You've got this thing called the shell down here at the bottom. It tells you what version of Python you're running. Thonny will install Python also, so it's not just an editor. It will go and the package will put one version, apparently 3.7.7 of Python as part of the installation. Over here is where you're going to write your code. You've got this thing called the assistant off to the right. We don't need either of those right now. We are going to try and make some plots in Python right now. So before we can do that, though, we need to install a library. Now, I've already done it with this version, so it won't actually do anything. It takes 3 minutes maybe. I just didn't want to sit here while we did 3 minutes of it installing. So you go to Tools up here at the top. Let me make sure we're showing up on the screen here. Yes. All right. So Tools, Manage Packages, and then it'll show a bunch of things you already have installed over here. But the one that we need for plotting is not one of those. So what we want to do is we want to install Matplotlib library, so LIB. Mat, so like math, sort of, but without the H. Plot, we want to make plots, and library, but only LIB. and then you can find the package from PyPy, so Python PI, and it should find it relatively quickly. You do have to be connected to the internet. I guess if you're watching this on YouTube, you must be connected to the internet. I suppose. All right, and so mine says installed version, so I already have. Actually, look, there's a new version, 3.3.2, and I have 3.3.1 installed. I don't know that there's a major difference between like the 0.1 and 0.2 because 3.3 is probably about the same. I could upgrade if I wanted to. Why don't we do that? It doesn't take very long. Yours will say install right here, and it goes out and it downloads this package, and it'll find my existing installation. This window, it doesn't always look like anything's happening, right? At least the cursor flashes, but once it goes away, then it brings you back here, and that's it. That you have installed the Matplotlib library, and you won't need to do that again unless you happen to look at it or you're troubleshooting something and find out, oh, well, they fixed that in 3.3.3. Then you could go back to the same process, find the same library, and like I did, there might be a little bit of an upgrade. All right, you can uninstall them if you need to. I don't know why you would ever need to, but they're not things that you have to do every time. So you don't have to, the next time you start up Thonny, you don't have to go and do this again. It's in your list. In fact, it shows up over here in my list of libraries that it knows about. All right, so we can just close that. So what that does is it gives us access to a library, and a library is just a set of code that's already written. So we don't have to go and write a bunch of code to do these plots. To use it though, in our code, in our actual program we're about to write, we have to tell our program that we want to use this library. So to do that, you use the command import. So we're going to import a library. The library that we want to import is Matplotlib library, the thing we just installed. I don't want the whole thing though, so this library has many functions inside of it. Right now, I don't want to go and install or use all of those functions. I just want to use the ones that are associated with pyplot, Python plot. So this dot pyplot tells the code that I only want this part of this library. I don't want the whole thing. You would be fine to just put import matplot library and not specify that you only want the pyplot, but it will create more overhead in your code, and I don't think it would ever show up as running slower. But if you had a lot of these where you just imported all of the entire libraries, then there might be some performance hits later on. For us, for what we're going to do, it wouldn't make any real difference. But we're going to do a good coding practice and only get what we need here. And we don't want to write this whole string of stuff every time that we want to use it. So we're going to say import that, but we're going to import it as PLT. So we're going to basically give it a nickname of PLT. So instead of having to write all of this, we can just write PLT every time we want to use it. All right. So that's usually you do this first. Usually you do any kind of imports that you want to have in your code. You do that up front versus some buried in your code somewhere. For one thing, it tells you and anybody else that reads the code that you've imported these libraries, and they need to have them on their machine if they want to run the same code. Someone else running this code, if they didn't have the Matplot library installed like we just installed ours, then it wouldn't run for them because the library doesn't exist on their machine. So you usually do that up front. A lot of times also there's an order that if you try to use a library and you haven't imported it yet, then you can have an error. So let's define some variables. So we're going to plot stuff, so let's just call these X and Y. So X is going to equal a list. There's a document out there. In Moodle, there's a document that is a kind of reference document that talks about lists and tuples and all these different kinds of ways to put data together. If you use the square brackets, it's a list. many times you're going to use a list, and that's what we're using here. So a list is just kind of like an array. You can add to it if you need to. It's not you can change it if you need to. There are other versions of these things that look like lists that you can't ever change. Sometimes that's important, but for what we're doing, it's okay to do this. And I say can't ever, I mean can't ever in that piece of code. So here we just have x values of 1, 2, and 3. So this is like our x-axis. And then y is another list. These will be the y coordinates of these points that we want to plot. Let's just make up some numbers. I don't know, 5, 3. You don't have to have spaces. I just like them to because they look nice. All right, so now we have two lists, one named x, one named y, and they are representing x and y coordinates of 3 different data points. So we still haven't plotted anything yet. To plot something, we need 2 other variables. And we can name these x and y, the PLT, all of these are things that we could name whatever we wanted to. These are common among other Python programs. So if you go look online for an example, a lot of times PLT, you're going to see this line a lot of times if it's something to do with plotting. And they're going to use PLT, although you can make PLT into anything you want it if you wanted to change yours for some reason. The rest of this has to be written this way because this is Matplotlib is the name of the library. PyPlot is the name of the little group of functions inside that library, so we don't have an option on naming those other things. At least not an easy option. All right, so fig, comma ax. These are 2 variables, same kind of thing where you can name them whatever you want to. So these are referring to a figure and a set of axes in that figure. And these are kind of the standard variable names that get used, but you could name them anything you wanted to. So it's going to equal, here's the PLT, so instead of writing all of this, we're just writing PLT, because we said we could do that. And then PLT, which is another way to say matplotlib.pyplot, has some functions inside it, which we want to use right now, which is subplots. So subplots are how we're going to generate the blank graph. So it doesn't know what's in it yet, but it knows that we could put many different little subplots on this one figure. So the figure is a collection of all the subplots. So we have to tell the Python code how many subplots we want to have. We just want to have 1. So we don't put just 1 though, because the actually there's several variables here. We're only using the first 2. So we're using the first one is I think it's the number of rows. Let me check. Yes, it's number of rows. So I want 1 row and I want 1 column. Put a space in there because I like spaces. And so this will tell Python that I want a figure that contains 1 plot. But you could have, and later on hopefully we'll get to a figure that has maybe 2 plots or 4 plots or whatever. So we could change these numbers, number of rows and number of columns, to have different numbers of plots in our figure. All right. Axes, so not axis. So the way it works is each figure can have many sets of axes, and each axis usually consists of 2 axes. So an x-axis and a y-axis make up a set of axes, and a set of axes makes up a figure. In this case, we just have the 1x, the 1y making up 1 set of axes that is the entire figure, because the figure only has 1 plot. We're talking about this set right here. If we have more than 1, we have to specify which one. So are we talking about the plot in position 0, 0, which would be the top left, or 0, 1, which would be the top right, if I had a 2x2 set of figures. We'll get to that later. All right, so I want to plot this set of axes, and I want to use the axis x, which is 1, 2, 3, and the axis y, which is 538. And so that creates the plot. If I ran the program right now, nothing would actually happen though, because there's one more thing. I have to actually show all of the plots. I'm leaving this as a empty set of parentheses because there can be values in here. Like I could select certain options on how to show these plots. But since I don't want any of those options, I'm just leaving it empty. I still have to show the parentheses, even if I want it empty. All right, so there's a button up here, run current script, or there's a run button there, or you can hit F5, a lot of different ways to run the thing. So it saves it. Probably if you're following along and typing this as you're doing it, it probably asks you where you want to save it. The very first time it needs kind of a location on your computer on where to save everything. And so it probably popped up a window on where to save this thing. So here's our little plot. There's 0.1 x1 y5, that's this 1 5. There's x2 y3, that's this set, and x3 y8, that's this set. And so there's our first little plot. And it pops up in its own little window. There can only ever be one figure in here, but I can have lots of plots on this one figure. All right, so that's the basic. I think we've talked through that well enough. All right, let's say that we want to plot this thing, but let's run it again. Notice there's no labels. There's no label for X or Y. There's no chart title. So a lot of times if you're making this plot for a report, then you need all those things. You need X-axis labels and things like that. So we can take our same code, and before we show the plot, we can put all those labels on. So we have to create the plot right here, and then we can put all these labels on it in between when we create the plot and when we show the plot. So we're talking about that same AX plot that we defined earlier. Again, AX is just a variable that we made up, but it equals a subplot as part of this figure that we've just called fig. Set. Anytime you see a dot here, that means that we're taking a specific command associated with whatever's on the left side of the dot. So AX has a set of commands that are associated with it. AX is this subplot that we defined up here. So associated with subplots are commands named set X label. So obviously if you kind of figure that would set the X label, then you're correct. That's a lot of the Python. The commands are created in a way that they kind of tell you what they do. You may not know how to use them. In this case, we need to put a parentheses and then single quotes. You might can use double quotes also. I don't know. We'll just name this X-axis, and then we'll close our quotes and close our parentheses. So you can already probably figure out what we need to do for the Y. Is the same exact thing except Y label instead of X label. And then we'll put Y-axis. Oops, just the parentheses. And then the title is very similar. Set title. And then we'll just name it something. Okay, so now the green text here, and so different editors are going to color code differently, but in this particular editor, green is going to be just a string a string of characters that is going to be displayed in this case. You can kind of see some of the Python commands, import and as. It doesn't know these commands, subplots and everything, at least this editor doesn't, because they're built into the library. They're not Python, like generic Python. They're built into part of this library, so they don't get highlighted. And we're going to show this plot, and we run it. And there we go. We've got our title. We have a Y-axis and an X-axis label. And obviously we can type whatever we want to in between these quotation marks to change the label. Let's try to create a Actually, let's just start over instead of creating a new one here. Actually, let's leave this first set and we'll make a new set. Let's call this X1 and Y1. So that we're going to have two sets of traces or two graphs on our same plot. Not two different plots, but two traces on the same plot. So X2, let's give it the same values for X so that they line up. And then Y2, we'll just give it some other values. Let's see, I don't know, 1, 4, and 2. There we go. We have two traces now on our, or well, not on our plot yet, but that we're going to put on our plot. We still need to create our figure. We can use those same variables that we used before. We are only going to create one subplot, so this line is going to be exactly the same. One row, one column. So it's just one subplot on our figure. And then we're going to put our two labels on there. So we're going to plot on that one subplot that we have created. X1, Y1. So that'll grab the first set of data. Let's go ahead and label it. We didn't do this last time. We'll just call it Series 1. We don't have any more descriptive stuff than that right now. Let's create the second one. So this will be the set of data that we called X2, Y2. And we will label that as Series 2. These labels only show up if we use a legend, which we'll have to turn on if we want it to show up this time. Last time we didn't turn on the label, a legend, because we didn't put anything as a label for our different plot, or our one plot we had. So that creates those two lines, 11 and 12, create the two traces. They're not shown yet because we haven't actually shown the plot, but that creates them on the plot once we show it. We also want to do our, I guess I could have let these stay, set X label, and then let's just call that the X-axis, and set the Y label. And again, you can name these whatever you want to name them. I guess we won't name this my first graph. This will be my second graph. Oh, we need a quotation mark. If we want to turn that legend on, that'll actually show Series 1 and Series 2, these labels for each of the graphs, because so far we haven't controlled their color or anything, so we don't know which one is which, other than if we go and track which ones line up with what points here. So let's turn on the legend. It's another one of those that has options that we could put in here inside the parentheses, but I'm not interested in any of them, so we'll just leave that off. And then we will show our plot. So assuming that we didn't make any errors, I hit F5. There we go. So there's the legend up here. It's showing that the blue line is the one called Series 1, and the orange line is the one called Series 2. Now, we can change blue and orange, solid lines, dots. There are a lot of different things that we can do to make the graph more custom. Everything on the picture here is customizable. Now, Thani actually gives you a button down here where you can kind of configure some of the things if you wanted to, but it doesn't give you control over everything. So let's go into the plot for Series 1. So there are more things that we could add here. For instance, color equals, and there are a lot of colors. I had to put the wrong thing. Equals. There are a lot of colors that you can use. Let me see if I can find the. I'll put this in the chat for YouTube. That link goes to, I don't know how many, a lot of colors. Everything from, I'm looking at black, gray, silver, but then there are things like lavender blush and corn silk and medium aquamarine, all these different things. So there are a lot of different colors that you can choose from by name. You don't have to know their color code. A lot of times you have to know a code, like a hexadecimal code or an RGB code or something like that, in order to define a color. The Matplotlib library has a lot of colors by name. So green, here we go. I have two parentheses. I already had a parenthesis there. So we could change the color for the thing, for instance. We could change the line style. So do we want a solid line or a dashed line? Same thing. Let's see if I can find the link for the line style. Is on that same main page, matplotlib.org. It has a lot of the things like this. There's loosely dotted, solid, dash dotted, densely dash dotted. There's all kinds of line styles that you can choose from. Let's just use dashed. You can choose from them by name. You don't have to have some secret code. You just have to know the name of it. You can change the line width. This one is more straightforward. It's just a number. So bigger numbers make the line wider. Marker, there are several different markers. Let's see if I can find the list of markers. There in the chat is the list of markers. Circles, triangles, hexagons, all kinds of things. Let's just use a circle. And then these, I don't know that you can name them. I think their names are shortcuts. So the circle marker shortcut is the letter O. I don't know if, yeah, it's letter O. What else can we change? Well, the color of the marker. So we changed our color for our line to green. Let's change our marker face color. We can change it to some other color, blue. We can change the size, marker size. It's a number, so it can just be 10. All right, I think there might be some other things that we could change, but I don't know. That might be all of them. Let's run again and see what we get. All right, so there's our dashed line. It's thicker. It's got circles for markers. They're blue. The line is green. And the circles are size 10 compared to the line, which was size 3, I think. Yeah, line width 3. So you can really get these things customized exactly however you want to. You just have to know what words to use: dashed, green, blue, what the different symbols for the markers are. Things like that. Obviously, we could go in and do the same thing for Series 2. I don't think that's super important right now. Let's see. There are other types of plots you can do. Let's see what we're doing on time. We're okay on time. One plot that you could do that we just did was just a line plot, right? So you just plot lines connected together. Maybe you want a bar graph. So the only thing that's different is, now some of these markers and all may not apply. Let's erase most of this stuff, because most of that's not going to apply to a bar graph, and I don't want to work through what does and doesn't apply. So if we change, instead of ax.plot to ax.bar, now we have a bar graph. Now, I actually don't know what will happen if we try to put a bar. Let's just run it and see. I don't know. It may not. Well, all right. So it did try. So Series 2 is a line graph still. It's a plot. And Series 1 is the bar graph style. Now, normally bars don't have two options here as far as the... well, I guess it does. So X is still what position along the x-axis. In this case, y is more like the height of the bar, so that's similar. Let's make them both into bar graphs, and it should make them different colors now. There we go. Oh, except they're stacked, so they're overlapped. So we probably wouldn't want that. We wouldn't want them exactly lined up with one another. We could change that with doing something like, let's give this one the odd numbers, 1, 3, 5, and this one the even numbers for the x positions, 2, 4, and 6. Now they'll be side by side. So there they are. So you can do bar graphs. Similar approach where x is the position along the x-axis for the bar and y is the height of that particular bar. You can also you might want to think about, a bar graph, that looks like a histogram. And it does, and you could force it to work this way, but there's actually a simpler way. There is instead of bar, there is histogram. Let's get rid of the second one here. And let's change our data up a little bit. So there's a function that's already built for creating a histogram. So let's just say that we have some ages for our data. And they're just going to be a random set of ages. They do not have to be in order. Whoops. Do need to be separated by commas, though. Let's make a couple more. If we don't have too many, then the histogram doesn't really do much. Let's keep making a few random, somebody really old in here. Some of the same ones. All right, so there's our ages. So we have a list. Again, it's a list with the square brackets. It's unordered, so it's not it's not organized from smallest to largest. And the histogram function will come in, and we do need a couple of other. We don't need the exact same set of options here on the histogram. So what we need is what are the data points? So ages are all the data points that we want to be in the histogram. And then how many little bins? Remember, histogram has a certain number of bins that you've sorted it into. Typically, the number of bins is somewhere around the square root of the number of data points you have. I don't know how many data points I have, but there's not that many, so I can't have that many bins. Let's say 4 for the number of bins here. We could have a variable and then put bins in here. Sometimes it may look like more work, but sometimes it is better to have variables defined as the value and then use the variable name whenever you want to plot or whatever. That sometimes makes it simpler. Like, for instance, I wouldn't have to go back, and if I tried to edit this, I wouldn't have to remember that the second number is the number of bins now. I could say, oh, that's the number of bins, and oh, here's bins. I could change it to 6 or 5 or 3 or whatever. So it's a lot of times it may look like more work, but it's more work up front, typing a little bit more, but it is less work on troubleshooting and editing and everything later. All right, what else do we need? We need the range. So I don't know if we leave this one out if it auto ranges, but oh wait, so look at this. I wanted to use the variable name range, right? But when I did that, it turned purple. What that tells me is that Python already has a meaning for the word range, and I shouldn't use that as a variable name. So let's just use R. R did not turn purple, so R will equal, let's just go from, I have a 98 and a 2. Let's go from 0 to 100 for our range. Okay, what else do we need in here? Oh, we could type the color. red. Let's do red. Surely that's one of the colors. There's a histogram type. So I don't know all the different types, but I know that I want this one to be a bar. Obviously, you could go look up all the different types of options for the histogram. And then we could have well, let's just take the defaults here and see what happens. So there's our histogram. We put in a lot of ages that were between 0 and 20 apparently, and then just a few of the older ones. But it's all jammed together. So let's add an option here. I think if we do our width, if we do a width less than 1, it will squeeze them in a little bit, so they're not touching each other. There you go. There's some gaps between them now. And so notice it's not landing on any even numbers here because I have a range of 0 to 100 and I only have 4 graphs, and so they're counting by 25s. Maybe if I did, I could change the x-axis. If I did 5, then maybe it would land on some of the there. They look nicer. And look, we just basically, I don't know, I just randomly typed in numbers, but basically I typed in smaller numbers mostly, and then fewer, and even fewer. All right, so we could do histogram without having to create it ourselves. You know, we didn't have to go in and order our data and sort it out and anything. We just told it how many bins we wanted, what the range was, and then told it to create a histogram with this operator right here, HIST. Scatter plot would have been a lot. I should have saved some of these older ones. It would be a whole lot like the line plots, except instead of ax.plot, you'd do ax.scatter. And so the only difference there is in basically instead of connecting all the points with lines, it would just draw the points. So that's the only difference in the two. And it has the same options of color and marker type and size and all that kind of stuff. One that's not as similar is a pie chart. You can actually make pie charts. Obviously, we don't need these ages for pie charts. Let's create, we don't need bins and range. We don't need this. The labels can kind of stay, although there's not an X, well, no, because there's not an X and Y axis. So we could leave the title, I guess. And maybe we'll leave the legend on there. All right. So we need some data. These are going to be activities that you might be doing. You might, well, I want these to be strings like words. So I need to put them in quotes. Eat, sleep, if I could type it. You might work, and you might play. All right, so those are our different categories for our pie chart. Our pie chart will have 4 different categories in it. And then we'll have the time spent doing each one of these things. And we'll just make these into a number. 3, 7, 8, 6. I don't know what they mean, but maybe it's hours a day. Average hours a day. We can change our colors of the different pieces of pie if we want to. I don't. It would define them randomly. I don't think it's random. I think it uses the same order every time. I don't know what the order is. But if we want to define them to line up with certain activities, then we can do that. Here we're using the shortcut. So R is red, Y is yellow, G is green, and B is blue. And the R we could type red, yellow, green, and blue. All right, we've created our plot. That can be exactly the same. We want a single pie chart in a figure, so the 1, 1, it still works. Now to create the pie chart, ax.pie instead of .plot or .scatter or .hist. We want to use time spent as the first variable. So that's the 3, 7, 8, and 6. So the actual numbers that get printed. Labels, for the different sectors are going to be the variable that we called activities. So these do need to line up. So eat needs to be 3, and sleep needs to be 7, work needs to be 8, and so forth. So those do need to be lined up with each other, or it'll be confused. It doesn't know any difference between what number associates with what activity. Color, again, we could go in and define the colors as R, Y, G, and B here, or we put that in a variable, sector colors. So now each one of those, and again, the first sector, eat, is lined up with 3, is lined up with red. So these do, the order of them does matter. It doesn't matter what order they're in, but if you want play to be blue and be 6 hours, you need to put those all in the same index position in these lists that you've created. Let's see, we could do a shadow. It's just on and off, or true and false. I guess if you don't put anything, it's false. If you put true, it does turn on the shadow. One thing a lot of times you want to do is explode, so pull one piece of pie out from the others. And this works the same way where there's a set. So I have 4 different pieces: eat, sleep, work, and play. So each one can be exploded a different amount, and these are percentages of the radius. So 0 for eat will not be pulled out. Let's pull out work. So work is the third one. Let's pull it out 10%, so 0.1. That's 10% of the radius of however big it makes this plot, which we could define that too. We'll do that in a second. Let's say the radius is equal to 1.2. I don't remember what the 1.2 is measured in. If it, it's not pixels, so I don't know exactly remember what 1.2 is measured in. We didn't ever calculate like 3 is what percent of this total. You could do that, so you could create the percentages yourself, but there is a auto percent that Python will calculate the percentages for you. So you turn that on, auto percent, and then you give it the format of how you want it to present the percentages. And to do that, it looks crazy, right? So what you're telling it here is that you want a decimal floating number. It's going to be a percent symbol after it, and these extra percents are telling you that it's I believe that's telling it it's a number. I don't remember. It shows that's how you format a string, basically. So it doesn't matter. The extra percents aren't telling you, the ones on the outside aren't telling you that it's a percent, but this percent symbol is telling it that it's going to put the percent sign out there. And the ones on that very outside are telling it that this is how I want it formatted. Well, let's see. Oh wait, did we show the plot? Yes. Well, we still have, this will be my first pie chart. All right, let's see if we got it right. Oh wait, no, we got something wrong. All right, so when you get something wrong, let's make sure this shows on the screen. Yeah, down here, it's gonna tell me, this traceback is like, where is something wrong? And it's telling me that in this line, I have written something wrong. So basically this line where I wrote everything at. Let's see if we can track down what I might have, because it doesn't tell me exactly what I did wrong, but I think it's because this is not in quotes. Oh, well, all right, so here's another thing. You have to spell your variables the same name. Up here, activity, put it this way, and there, we'll just make it spelled the same. Oh, color equals sector colors, because I wrote, well, no, this is actually in the pie plot and the scatter plot and all of those, you are coloring a line, a single line. Here, these are the colors, plural, of the different pieces of pi. So this is just the variable that gets used in pi is actually colors, not color. All right. Eventually, oh, we got it right. All right. Oh, well, there's a little bit of issue here with my title is overlapping the label for the sleep section. It put in the number percent sign and it calculated all the percents of each one of these. Put the legend up there. We told it to do that. The title, we really need to move the title up. And there is a way to do that, actually. If I could just remember how to do it. Let's see. So sometimes it will... Oh, wait, that's just the scale of the whole thing. That one doesn't do anything. It just moves the whole thing left and right. Could make it tiny. That's not what I want. Well, reset. I'll have to look and see. For now, we can fix that by just turning this off. Oh wait. Oh, I gotta remember which program. Well, we'll just erase it. There we go. One thing we could do is rotate the start angle for this thing so that it doesn't put a label up at the top. We can rotate the thing around. I think that's called start angle, actually. Let me see if I can find it real quick. It is start angle, yes. All one word. I'm looking at the reference sheet, so if we started at 90, then it should rotate it around. And now there wouldn't be a label up there at the top that would overlap it for us. So you can change where you start the pi at. Okay. Up until now, all of that was a single subplot on our figure. Let's look at how to make multiple subplots on the same figure. And then I think that'll probably get us through what we need to do. There's a couple of things that you need to know about two different approaches to plotting. One is called stateful and one is called stateless. We're going to do the stateless approach. That's the one that we've been doing. There are advantages to using the stateful approach, but it's a little more complicated, and basically what it does is it only lets you edit one piece of your plot, your figure, at a time, and then to edit a new one you have to change the state that you're editing. So it adds one little parameter in most of the commands. You know, what state are you editing right now, state 1 or state 2 or whatever. I think it's simple enough for the plots that we're going to do the stateless approach, where we don't really have to worry about which state are we currently editing. And that's what we've been doing. I think it makes enough sense that it's not going to be a problem. So let's leave plot show in there and that. So we know we need to start by importing the library, and we know we need to end by showing the plot. So we'll leave those in. All right, we need some new data here. Let's just make some X and Y data. We won't worry with the spaces this time. Let's go to 5. Let's have just some random numbers here for the Y variable. Can have negative numbers. We do have to have the same number. So 1, 2, 3, 4, 5, 6 sets of data. So those are our X and Y data points that we're going to have, our sets. We'll use that same set of variables for the figure and the axes. But there will be one difference. So last time we did PLT, that's the library, or the PyPlot part of the library. We're going to plot subplots, but this time we've been using 1, 1 for one row and one column. But let's do 2, 2. this will give us 2 rows and 2 columns of plots. So now we have to be specific about which plot we're talking about when we are editing them, because there's going to be 4 plots on our one figure. All right, so the most computer programs, including Python, are indexed starting at 0. So the first element in our, how do we reference our first of anything is index 0. So the first row and the first column, that top left corner, is not 1, 1. It's actually 0, 0. So axis 0, 0 is actually the top left plot in our set of 4 little plots. We're going to plot this thing, and it is going to just plot X, Y data. And we'll use the circle marker. Actually, the circle marker with connected lines. So to do that, we didn't do that last time. It's, well, I have to say, I just have to tell it 0 and do a little minus sign after it, and that will use circles for the data points, and the little minus sign shows that it will draw lines between the data points. I think is what it shows. I'll have to look that up. Let's see. It's right here. Circle. Well, I don't see it right away. I'll make sure about what the circle minus means. The circle means it's going to be circle. Actually, let's just leave the minus off and see what happens. All right. Sometimes that's the easiest thing, is to run it and see, oh, that's what that does. Because there are a lot of little options. So we're still talking about this plot up here, the one in the top left corner, that will be in the top left corner. And we're going to set the label for that as, I don't know, top left Y axis label. Okay. And so that's one plot, but we created 4 plots. Well, we created positions for 4 plots, but we only made 1 plot so far. If we run it now, I did. Guess I was talking and typing at the same time. All right, so there it created the other spots for the other 3. Okay, and look, so I have the dots here. If I do the circle minus, I think that does connect the dots together. Yeah, it connects them together. All right. I thought that's what it was doing, but I wasn't certain. So sometimes you just have to do it to find out. All right, so let's do one of the other plots. So we use the same axes variable, but we talk about which particular one. So row 1, which is actually what we might call the second row, comma 0. So this should be the one directly underneath the plot that we just did. Let's make it a bar chart. And it'll use the same sets of variables, X and Y, because we're not going to make another set of variable for this. Let's give it a Y label also. We still have to tell it which one we're talking about. Oh, you know what? I did set label. That should have been set Y label. I didn't even pay attention to what it actually did. This will be the bottom left Y axis label. Okay. And when you're writing larger pieces of code, it's a good idea to write a little bit and do a run to see, does that much work? Yes, that much works. And now I do notice that the Y labels are on here. I didn't even notice if they were on there the first time because I didn't write Y label. All right, so that's what we expected to happen. That's good. We could maybe change the color. Now it's got red on there. All right, let's do the bottom, or 0, 1. So that'll be the top row and the second column, what we would call the second column. So that'll be 0 for the first row. Whoops, that's 9. and the second column is actually 0, 1, so it's 1. So we start counting with 1. Start counting with 0. This one, let's make a scatter plot. So it's just scatter x comma y. Why don't we copy this, change this to the right thing, y label. This will be the top right, and then let's run that. Now see, we're running over the other one right here, so we got some overlap between that label and the next graph. I think there are some options on how to not make things overlap. Let's go ahead and add that. This might have fixed our pie plot earlier too. I forgot about that. Let's see if this fixes this. Plot, no, not PLY, plot. So PLT is the reference to matplotlib.pyplot. PLT tight layout. I don't remember the options, but tight layout should at least spread everything where it doesn't overlap, but keep it close together. So let's see. There we go. See, it's not spread out too far, still tight, but this y-axis label might be off your screen. This y-axis label is not overlapping the plot like it was before. We've got one more of these to fill in, and it would be the 1, 1. So this is the bottom right, and let's just make it a plot, but let's plot it backwards. So y comma x. So x and y are meaningless to Python. It doesn't know that x means the horizontal axis and y means the vertical. It doesn't know any of that stuff. So it just knows that x is 0, 1, 2, 3, 4, 5, and y is these other numbers. Let's plot our. Actually, let's do this one. Bottom right. And so this one will look kind of funny because we've plotted it sideways, basically. And we didn't put any markers on it or anything. Here, the scatter plot, by default, does not connect the dots. And it just uses circles. So hopefully that gives you a reference point. The 3 different references from the matplotlib.org for the different color names and the line styles and the marker styles. Those are useful. I'll link those in the description of the video too, so that they're easy to find. I think the chat goes away once I am not live streaming anymore. So I'll put those in the video description. They're on Moodle too, or at least I think they are. They're in a document that's on Moodle. So I think that gets us far enough along to go back to our, let's get this off the screen. Go back to our multimeter and let's see if you want to see. I'm going to take this apart and see if I can find a fuse in there. All right, had to get a screwdriver. So if you ever are certain you're doing correctly, but you're not getting any current measurements, there's a good chance that there's a blown fuse in your multimeter. So let's look at these and wow, that one's what to. This screwdriver was a little too pointed for that screw. Actually, that one may not have had to come out anyway, though. Oh, yeah, there's also a battery in there. It looks like that's a pretty old battery. This one didn't actually have to come out. That's just the battery, because remember, the multimeter a lot of times does have to provide a current in order to measure a resistance or something like that. These two, let's see if we can figure out how this opens. There it goes. I don't see any other screws, but there's something that I don't want to break. But I also am not certain. There it goes. It just has a little snap in it. All right, so, well, here's a giant fuse. That fuse is the 10 amp fuse. Kind of hard to tell if it is, actually it's an 11 amp fuse, it says. Oh, wow, that little post is broken there. I don't see a separate fuse though. I only see this one fuse. But a lot of times there'll be a fuse similar to this. This is a very beefy fuse for the 10 amp side of things. I don't think it would use that same fuse for this size, but maybe it does. It's possible, I guess, but I don't know why it would. But I don't see a separate fuse that's changeable anyway. And this one, I don't even know if I can get it out of there easily. There it goes. So if I had my multimeter, I might could check continuity for the thing. I guess I'll have to get another multimeter to check to see if this is blown or not. But these things, this is not the typical fuse that you're going to find that in most multimeters. This is because this one can usually measure up to 10 amps. I don't think I ever measured anything that would have blown this fuse, but it's possible. But I would have to check. A lot of times what you'll see in a fuse is a little single element inside there that you can actually tell that it's burned up. Let me see if I have one that I can show you. Here are other fuses. Let's zoom in closer. All right, let's see if we can find them. So this style right here is typically what you'll find in a multimeter, and you can see it reflecting off there. See that single piece of metal inside there? If it's blown, it will actually be broken right across that thinner part. It'll be in half. I don't know if I have a blown fuse that I can show you anywhere. Here's another style. This one's usually not the style that's in a multimeter, but it has the same idea. There's a little loop inside there, and it'll be blown apart in the center of that little loop a lot of times. You can always check, if you have a working multimeter, you can check for continuity across the two ends or across the two ends here. And if it doesn't beep, if there's no continuity across there, then it's blown. But most of these you can actually see there's a piece of metal inside there that will be broken in half. Maybe even a little bit charred, but usually you can tell that it's broken in half. I wish I had a blown one I could show you, but I don't think I could find one really quickly. I think I will change the battery here, get another multimeter, make sure that this fuse is fine, and maybe go recheck why I wasn't getting any current measurement. But we're not going to measure current probably at all in this course. Maybe, but I don't think we are going to measure it much at all. All right, next time we are going to look at some standards. So like I mentioned earlier, how do I know if this multimeter is right? How do I know if the resistor was the right one and the multimeter is off? How do I know what a standard measurement is? So we're going to look at that. Some more Python. We'll walk through some more Python examples, and then just numbering systems in general. So that might seem a little abstract, but it's important for some of the stuff we're going to do later. But that'll be on Wednesday morning. All right, I will see y'all at least on Wednesday morning.